Hello all. Today's video is regarding some of the guidelines which has to be followed while a container or a Docker image is being created. As we have spoken in our previous videos, container-based deployment of applications inside a vehicle are becoming one of the favorite way of deploying software inside a vehicle. So, with this being said, the containers which are deployed should undergo some what do I say? Some kind of they have to have some kind of restrictions with respect to security, with respect to resource management, and many other vulnerabilities should not be there in those container images, or else the entire car can be compromised. So because of this reason, some of the guidelines have to be followed, which we'll be discussing in this particular video. For a generalized understanding, I'm just considering Docker runtime and Docker daemon over here because most of the other container runtime architectures are quite similar to how Docker works. So I'll do it in that way. And though this particular, what do I say? Uh, though this is something a new topic in the automotive domain, this is something which has been addressed quite extensively in the other domains, mostly where the DevSecOps is quite active with respect to deployment of software, mostly in cloud. So most of those guidelines will also be kind of relevant even in this particular automotive use case. So let's get started. So this is one of the basic architecture of Docker. You have a Docker client, which is over here. You have a Docker host, which has a Docker daemon. Inside this, you have many of the containers and you have many of the images, and you basically have the Docker registry. The communication between this Docker client and Docker host is basically a socket-based communication. Now, one of the fundamental thing over here is generally the communication between the Docker client and Docker daemon are, as I said, are socket-based communication, TCP communications. Generally happening, these are not secure; these are insecure communications. Now, in order to avoid a man-in-the-middle attack, one of the first precaution which has to be taken is it should be a secured communication with the public-private keys. So we need to go for an HTTPS based communication rather than a general HTTP communication to avoid any uh, vulnerability, to avoid any kind of security glitch or something. So this could be one of the initial precaution which has to be taken when any application which is trying to use the underlying container runtime, because container runtimes are quite extensively being used, let it be Podman, Docker, or whatever it is. So this is one of the safety requirement or security requirement which has to be considered to avoid man in the middle attacks. Now, second thing, generally what happens is containers, if at all, some of the container runtimes which run as root, Docker is one such example, and there are other container runtimes which doesn't run as root, so which is like Podman. So say you have your container runtime running as root, then the containers running on the container runtime also has root privileges, which is actually not good, because in the use case like which we are discussing, most of the third party applications will be deployed onto the vehicle, and them being deployed having root privileges is basically an issue. So in order to kind of avoid that, first of all we have to look for a non-root container runtime, and another precaution which we have to take is that the containers which are being created should not have the root user group. It should there should be a separate user group which is not having the privileges as of a root user group. So while you are creating a Docker image itself, that has to be kept in mind. So this is one such example. So using an unprivileged root user. So when we generally create a container image, when we create an image, so we simply say that use this Ubuntu, and we simply say what are all the things which you have to install, but we never generally add a specific user group and specify that this is something which is not running as root. So in this example, there is this container image which has been, this is the Docker file for a image where we are specifically saving the group which is basically Komal, which is my name, and we even say that the environment is home slash Komal. Now if at all we have to run this particular Docker, we use the username as minus u Komal, so that this particular container, when it runs, it is not having the root privileges, it is just having a user privileges, which is an unprivileged user. So this is one way of avoiding any kind of privileged access provided to a container. The second way of doing is, when we are basically running a container, we have to say that this particular container does not have the access to have any new privileges. So while you run the Docker run itself, we need to say that in the security options, you have to say that there are no new privileges for this particular container when it starts running. Similarly, when a container runs, basically it will have a lot of capabilities. So instead of running a container as such, it is better to drop all the capabilities which the container has by default and add the specific capability whichever you want for that particular image when it runs. So these are some of the small guidelines which, when followed, will reduce the attack surface area, because this takes care of kind of few of the general attack possible scenarios which are out there. And there might be some containers which are simply running, but they don't need any kind of inter container communication networks. So why do you give access to the container networks, like maybe this your Docker bridge or whatever? That is not needed. If a container doesn't need it, then there's no point in having the particular network access for that specific container. So you have to kind of create a dummy network. You have to link your particular image to that particular network, and so that you basically isolate it from the rest of the system, so that this container does not interfere with the other containers which basically have a requirement of communicating with each other. So this is another such precaution which has to be considered whenever it is useful. And another main resource constraints when a container runs is that any person should not run some malicious software while he is basically running using the container. So means, say he runs a fork bomb, or say he tries to do some kind of crypto mining on a vehicle using a container. So this might be quite scary, because this will take a hell lot of resources, and the container as such is not allowed to access those many resources. So one way of basically controlling this kind of restrictions or resource consumptions for an image when it runs as a container is by restricting it via the C groups. So using C groups, basically we can restrict the CPU memory, the PIDs, how many PIDs can run, what kind of devices it can access, similarly the block IO restrictions and all. So using the C groups and multiple flags available in Docker or in other popular runtimes like Podman and all, we can basically restrict the amount of resources a particular container can use while it runs. So this is another point which has to be considered while creation of container and while deployment of containers. And the access control mechanisms. So in general, we have the discretionary access control, where we speak with respect to accessing a specific resources like chmod, chown. So these kind of restrictions which we generally put. Other than that, we have this mandatory access controls. So mandatory access controls are some things where we create a profile, and the profile is enforced while a particular container is kind of running, while the image is running. So generally there are two mandatory access controls, which is AppArmor and SE Linux. So AppArmor is generally based for Debian images, and SE Linux is mostly for Red Hat and Fedora. Now say we take the example of AppArmors. So this is how an AppArmor profile looks like. So in the AppArmor profile, we say that there is this container which I'm sorry, there is this image which I'm running, and so there will be some specific file. The allowing the executable to run is something which only this particular binary has. Similarly, we can deny some executions of the file, which we can basically write over here that slash bin slash dash or slash bin slash sh are denied to be basically accessed. And similarly, we can write some kind of capabilities which this particular container can do when this particular when this particular AppArmor profile is applied on it. So say this is one AppArmor profile, say xyz.profile. Now this is how we create an AppArmor profile, saying that this binary execution is allowed, these are the paths which are basically denied, and these are some of the capabilities which this particular container has. And how we enforce it? You basically run this docker run security options, you give the AppArmor, and you give the corresponding profile name, and you say that I want to apply this particular profile name on this specific docker image. So once that specific docker image is basically um, uh, is inheriting the AppArmor profile, it basically behaves in such a way that all these profile restrictions, whichever they are provided, are basically enforced into that particular container when it runs. Similarly, there is this SecCom profile. SecCom stands for Secure Computing Profile. So here basically what we say is like it is basically like a firewall which restricts the kind of calls which the system can the container can do to the system, to the kernel and other things. So it basically restricts the type of system calls the container can do. So using this unnecessary system calls from the container to other regions where it doesn't have access or doesn't need any access can be greatly reduced, which basically reduces the overall attack surface for the containers. And there are few other best practices which when followed basically makes the scope of the attacks on the container can reduce as much as possible. So one such best practice is to use a minimal image. So what does a minimal image mean? Say we have to simply run a say Python file. The container basically runs a particular Python file, and now in order to run a simple Python file, we can basically use the base image as Ubuntu, or we can use a base image as a Alpine Python image. So Alpine Python image basically does the job for us. There is no point in taking Ubuntu 18 or Ubuntu 20 as a base image, because if we take images like Ubuntu, then basically what happens is you are basically increasing the attack surface, so that there is a high scope of some vulnerability to be there. And if your use case is fulfilled with a simple Alpine image, that should be good enough for you. That is one thing. Second thing is, when we are basically creating a particular Docker image, the generally how people create is they simply say Ubuntu 18.04 latest. That is actually not the right way of doing, because when you have created the image, you don't know, okay, you have taken the latest image which was at that point of time. Going forward, maybe 6 months down the line, that might not be the latest image which you used back then. So it is better to give the tag properly rather than giving the tag as latest. So that is another best practice which followed is actually good for you. And another one is to remove or reduce unnecessary packages from an image. So say you have a base image and you have some packages which you don't need, then you basically don't need those packages. It's better to remove it. And apart from that, storing of secrets, storing of passwords in Docker file is something which is not encouraged. Similarly, pulling the images from a secure and verified Docker registries is highly safe for you rather than pulling from any place. so that would be of risk for you. And there are many tools which basically kinds of helps you out in automating this thing. So as I said, this is something new uh, for an automotive use case, but this is not the case in industry because it is already being extensively used. So DevSecOps is basically the field which deals with these kind of verifications and validations. So they use multiple tools. So Linus is one such tool which basically used for hardening the operating system and saying which are all the vulnerabilities which are there in the host operating system. Second one is with respect to audit. This is another tool which basically checks the policies of the Linux. Third one is Bane, which eases your which basically creates AppArmor profiles which you can basically apply onto your container images, and you can have secure containers which are well protected because of this AppArmor profiles. Trivy is a tool which scans the vulnerabilities inside a container and the image. So it looks for any of the vulnerabilities, any of the bugs which are out there, and it kind of gives you suggestions on what to do. And Dockly is a tool which just makes sure that you are using the best practice while you are creating a Docker file. So that is what Dockly is. So these are some of the tools which I have come across. These are not the only tools. There are multiple tools other than this, and there are multiple alternatives for each of this tool. So if you guys are interested, maybe you can look into that. That would be of interest to you. So these are some of the overall views with respect to the guidelines which has to be followed while a container is being created and is being deployed into an automotive environment. So these are some of the guidelines which I found are interesting. Anyways, thank you for your time. Thank you for listening. Thank you all.